Yay. Nice. Okay. I'm going to reset the timer again. All right. Hi, I'm Paul. Hopefully it's recording now. And this is joint work with Amit, Sahai and Varun, Sivashankar on a relinearization attack that we just like to throw out there on LPN over large fields. Let me hit the next slide. Oh, I think I have to hit this thing. No?
The clicker should work. Green should be advanced.
Nope.
No?
I think I'll just click it. Okay. So why do we care about attacking LPN over large fields? LPN over large fields is one of the 4 or 3 assumptions, depending on which paper you're referring to, that implies indistinguishability obfuscation from well-founded assumptions. And this was the work of Jane Lynn Sahai 21, and I believe there's a follow-up work that removes the lattice assumptions. So that's an IO candidate from just PRGs in NC0, LPN over large fields, and bilinear maps. So LPN over large fields it's a really old mathematical assumption or conjecture, the hardness of it, the search problem from coding theory. And it was really adapted in this IPS09 paper for cryptographic purposes. So it's an important assumption, and it's important to understand security. We actually only know, in the setting that's relevant to I/O, the best known attack is this so-called naive attack, which I'll explain later. And it's a sub-exponential guessing algorithm. It's the state of the art. There's some other attacks, but there's really nothing much better. So we decided to try to come up with a Grosvenor basis approach or relinearization approach to attack this LPN over large fields. So there's us with our attack, and there's LPN over large fields with the high ground. And we all know, if you've watched episode 3, how it ends. Well, we asked the questions, will a very particular, we're not saying that the approach itself will fail, where we give a concrete approach and it doesn't work under some reasonable assumption. And we're still in exponential time. So with this approach, and we don't even meet the naive attack. So great. Let me go to the next slide. So let me describe LPN over large fields. You're given the setting A, AS plus E, where A is going to be this uniform random matrix from FP, and the number of samples is M, the dimension of the secret is N, and P you can think of as a lambda bit prime, but you can really think of it as any prime power. And for some sparsity constant gamma, we're going to sample the error in a Bernoulli-esque style. So with some probability n to the minus gamma, we're going to sample a random FP element. And with probability 1 minus n to the minus gamma, we're going to sample 0. So it's a really sparse error. It's 0 almost everywhere. But where it's not 0, it's uniform random. And in our setting, we're going to think of m, the number of equations, as some n to the 1 plus alpha, where you can think of alpha as a constant between 0 and 1. And the search problem is to recover the secret S from A, AS plus E. And you can prove that there's going to be a unique solution S with high probability for sufficiently large M. And this will be true in our case. So there's a unique secret that you're trying to recover in the search problem. Okay, and just to motivate again some other use cases of LPN over large fields in cryptography, there's the classic work of Aleknovich, which does it over F2 to get PKE, and then it's extended in the work of Applebaum and others to FP. Though, and this only works when the sparsity constant is larger than half. If it's not, then we don't know how to get PKEs. And then there's also works related to oblivious transfer and OLE for correlation generators. That was by Boyle et al. And there's also IO from JLS. And just as a note, LPN over F2, I think, is used for a lot of different things. It's used for max authentication schemes. That's the work of Lubashevsky et al. And there's, I believe, there's some like constant, like very efficient primitive stuff from LPN as well in general. So, and oh yeah, there's a search to decision reduction. So, and I believe that's attributed to the same authors that do the search to decision for LWE. Okay. So what's the known attack landscape for LPN over large fields? There's no known reductions between LPN over large fields and learning with errors. Principally, the principal difference between these two are the error distributions. So in one, we have this really sparse Bernoulli-esque type error, and in the other setting, you have usually discrete Gaussian, though there are variants of LWE, like learning with rounding and learning with binary LWE. But the principal differences between all of these are the error distributions. And there's this folklore attack, which some people call the naive attack. And how does the naive attack work? One way of thinking about it is, suppose you were given an LPN oracle, and you just ask for n samples, and you pray and hope that all n samples are error-free, and you just run Gaussian elimination to solve for S. If you have n error-free, you're just given like literally error-free linear equation to solve, and then just solve for S. And to check that this is the correct S, you can sample another n and just check that indeed when you subtract out A times S, you get something of small error weight. So that's one way of attacking. This is the folklore naive attack. And this works in this low noise rate regime. And when I mean low noise rate, I mean inverse polynomial, whereas contrasting that to high noise rate, where you could have as large as like, you think of like 1/3 fraction of all your error coordinates have errors. So that's like a constant noise rate. So in the low noise regime, this is pretty much the best that we have, and it's sub-exponential just by a probabilistic argument. There's also these information set decoding invariants. These work, I believe that should be a T, not a CS16. I think that's Torres and L. And there's many other works that improve on the original Prange 62 paper. But this is basically a syndrome decoding solution algorithm on the dual version of LPN. And these are, depending on your noise and sample regime, are also sub-exponential. But in our setting, again, we're going to be in the low noise rate setting, and samples of the number of samples m is about n to the 1 plus alpha for alpha between 0 and 1. Again, the folklore attack does better. And in the high noise rate setting, we have this BKW algorithm, Blum-Kalai-Wasserman algorithm, and it actually requires sample complexity sub-exponential as well, but there's also a scaled down version where instead of 2 to the n over log n, you'll get 2 to the n over log n, and that's due to Lyubashevsky. And in all this landscaping, we just don't see a Grosvenor basis attack, and so we're going to throw one out to you all and see whether or not it works. And spoilers, we're here, CFAIL. Right, okay. So again, our regime is low noise rate, n to the minus gamma, sample complexity m equals n to the 1 plus alpha for some alpha between 0 and 1. And in this setting, again, there's no known attack that does better than the folklore attack. And the objective is to find a better sub-exponential attack via Grosvenor basis approach. And we really pitch it as a relinearization approach because we're going to think of it in that framework as well. The punchline is we didn't succeed. We don't even meet the folklore attack. Our approach only yields an exponential time attack, assuming something about the system we propose, this system of polynomials we propose. It's a conjecture about semi-regularity, which I'll get into later. And as a note, it's just like widely believed. So that our polynomial system we're proposing is semi-regular. Okay, and then we'll discuss the approaches we tried, some other things we tried, and some open questions and takeaways. Okay, so I'm going to back up because I'm not sure what everyone's background is, so we're going to start from ground up. What is linearization when we speak of linearization? This was a technique introduced by, I think it was introduced by Kipnis Shamir in '99, and then really made popular by Aurora Ge in 2011. And the idea is, suppose you have like a quadratic system or any d-degree system. What you're going to do is you'd like to reduce the problem to solving a linear system. And for example, let's say we have the monomials x1, x1, x2. We're going to linearize them by just mapping them to a new set of variables, y1 and y12. So in equations such as x1, x2 plus x1 plus 3, you're just going to replace the corresponding monomials with these new sets of variables. And if you start with m degree d equations, the number of present monomials that you have is going to be the number of new variables you have. And just by a stars and bars counting argument, we know there's at like n plus d choose d many such monomials. And generally speaking, how the argument goes is if there was a unique solution to the original system, this higher degree equation system, and the number of equations m is sufficiently larger than the number of monomials or the number of new variables, then the linearized system has the same unique solution with high probability. This is kind of the argument that Aurora makes, and this sort of argument should work in general. Okay, and then as a result, once you've linearized, you have a linear system in n prime many variables, and as a result, solving is just by Gaussian elimination, linear algebra, and you're going to have a runtime of approximately like n prime to the omega, where omega is the linear algebra constant, where we know it's between like 2 and 3, less than 2.4. Right. Okay, so that's the linearization technique. And here's an example of an attack due to Aurora in 2011, where the attack is on binary LWE. Let me describe the difference. Binary LWE is just, we're going to change the error distribution. That's the only thing we're going to change. And the error is going to be between 0, 1 error. And every coordinate in the error will be sampled from a Bernoulli with some parameter tau. So with probability tau, it'll be 1. And probably 1 minus L will be 0. And the goal is to recover S. And Aurora set up this really simple equation system, M equations from I equals 1 to M, just saying that they know the error is 0 or 1. So remember, so what is B here? B is AS plus E. So you're just saying, I know every error is 0 or 1, so if I take the product of BI minus AI inner product S minus 1 times BI minus AI inner product S, one of them has to be 0, so it has to be 0 mod P. And now we have m degree 2 equations in the secret S1 through Sn. We linearize, so every variable Si becomes Yi and every Si Sj become Yij. The number of linearized variables is order n squared. And roughly speaking, they show that if m was sufficiently large, like some omega of n squared, it's for sufficiently large constant, you get a polynomial time recovery. And then Sun, Tabuchi, and Abe revisited this hardness, and they show sample time trade-off for samples where you don't actually have quadratically many samples. You have like some subquadratic amount, m equals n to the 1 plus alpha, and they characterize the hardness of this approach, of binary LWE against this approach for various settings, including non-uniform Bernoulli. So, and the reason why I mention this is we're going to basically be using some of the stuff that Sun, Tabuchi, and Abe do in the 2020 paper. Okay, great. Okay, so in general, what happens when you have smaller sample complexity, say m approximately n to the 1 plus alpha, where alpha is between 0 and 1? And generally speaking, you don't have enough equations for the linearized system to have a unique solution. And the goal is to generate more equations. Okay, and how are we going to generate more equations? We're going to do this thing called degree D Macaulay expansion. And what is degree D Macaulay expansion? Let's say we start off with a set of equations f1 through fm. So that's this first set up there. Oh, yeah, I have a pointer. F1 through fm. Then what we're going to do is we're going to multiply every equation in this system by all monomials of up to degree D. So we're going to add in all the equations of the form x1 times f1 and then x1 times all the way up to fm, We do it for x2 and then x1, x2, and all the way up to all total degree d monomials. And we're going to consider, one can view this entire set system as a matrix just by writing out the coefficients, coefficient vector, and we'll call that the Macaulay matrix. And sometimes when we refer to the rank of the system, we're referring to really the rank of the Macaulay matrix. Okay? Right. And why are we doing this? The rough intuition, and it's also, you can find this in Santabuchi and Abe's introduction, is roughly speaking, if there's a unique solution to this polynomial system, say the secret S, then we know that Hilbert's Null-Stellensatz says that the ideal generated by this polynomial is equivalent to the ideal generated by these linear equations that exactly pinpoint S. The varieties are the same. And this set of generators is essentially our Grosvenor basis. It's equivalently viewed as our Grosvenor basis. And if these two ideals are equivalent, then we know that we can rewrite every one of these generators as a polynomial combination of the F1 through Fm. This is just by definition of the ideal. And if you just look at this right-hand side, what is this right-hand side? It's about summation of polynomials times Fi. What are polynomials? They're just sums of terms which contain coefficient times monomial. So you literally have a summation of monomials times Fi. And all we're saying is expand the system enough that you recover a way to recover xj minus sj from the original Fi. So we're just going to expand up to some degree such that we can recover this Grosvenor basis x1 minus s1, xn minus sn. If we do that, then the Grosvenor basis pops out. And if you just look at this Grosvenor basis, it's equivalent to knowing a solution. You know the S1 through Sn. So that's to motivate why we're doing this Macaulay expansion. In fact, multiple works, including, the pointer died, but it's okay. Daniel Lazar.
That's on brand. We programmed that in.
Yeah. Daniel Lazar, sorry, I'm just pulling up the timer again. Daniel Lazard in '83 showed that computing Grosvenor bases for homogeneous polynomial system, homogeneous meaning that every polynomial is, every term is of degree d, is equivalent to performing Gaussian elimination on a series of Macaulay matrices. So, and in fact, like these algorithms that you might see that compute Grosvenor bases like F4 and F5, one can view it in this format too. Okay, so back to our setting. What are we going to propose? Well, let's first recall the setup. The setup is, again, we have this matrix A, and then we have B equals AS times plus E for this type of error distribution. And we're going to solve S. And how we're going to solve S for, we propose a quadratic system of equations to attempt to solve for S. Okay. And what is our approach? Well, we can't take the Aurora-Good approach where we say that the error, because the error can be anything from FP. So we're going to guess whether an equation has error or not. So if I highlight an equation is of the form AI inner product S plus EI equals BI. And I'm going to define these indicator variables alpha I such that there'll be 1 if the error is 0, and 0 if the error is non-zero. And what does this mean? This gives us M equations of the following form. Alpha I times AI inner product S equals alpha I times BI. So if there's no error, then it's just AI times S equals BI. We know there's no error. And if there is error, well, both alpha I equals 0, so both sides of the equation are 0. So it holds in all cases. So as a recap, we have n plus m variables, n for the secret, and m for guessing whether or not an equation is error-free. And this gives us this, this gives us our first m equations. And then we're going to, of course, say that alpha i's have to be 0 or 1. So that's the next m. And of course, if we only had those two equations, you could set all the alpha i's to be 0 and like set your secret to be whatever. So we need to pinpoint a unique solution. We're going to add one extra equation, this linear equation, that just says we're going to guess the number of error-ridden equations t, and say that the number of equations, the number of error-ridden equations is t. So that's the last one. So the number of initial equations is 2m plus 1. Okay. And if we just naively count, we'll see that we have, at what degree of expansion do we have more equations than variables? Well, we need degree of approximately root m. And if we, so this is assuming full rank of the expanded system. Then we see that Gaussian elimination on an order root m degree expanded system takes time like e to the order root m, ln m. So this is sub-exponential TAC, and this sounds really nice, but obviously this is assuming full rank, and that's not true for Macaulay systems. So the question is the full rank assumption valid? And the question is, what degree of Macaulay expansion do we actually need so that the linearized expanded system polynomials has full rank? And it actually turns out that if we assume that this polynomial system we just set up, so I call it F with these 2m+1 equations, if we assume this polynomial system is semi-regular, which I'll explain in the next slide, then actually we can show that order m degree expansion is necessary. And if that's the case, the runtime becomes exponential. And it's, yeah, not very good. So what is a semi-regular polynomial system? I'm just going to give, for our purposes, like 2 main points of semi-regular polynomial systems. One, they're polynomial systems for which we can characterize a runtime upper bound for like the number of field operations we need to compute the Grosvenor basis. And this is because semi-regular polynomial systems have a characterization for the Hilbert series that's associated to the ideal generated by the system. And the second point is that, generally speaking, we believe that random overdetermined polynomial systems are semi-regular. So this is related to an open algebraic geometric conjecture of Froberg's, and I believe the reference for this it should be Keith Pardue's paper that relates this back to Froberg's conjecture. So and when I mean random polynomial systems, I mean you think about every coefficient in the polynomial being sampled uniform randomly from the field. And so I'm going to kind of give the definitions backwards because we don't want to get into all the details, nor do we have time. So assuming a polynomial system is semi-regular, then we can characterize the attack complexity by computing this thing called the degree of semi-regularity. And if we have this thing called the degree of semi-regularity, this lemma by Albrecht and Bardet et al. Show that the dominating term is this binomial coefficient, n plus degree of regularity minus 1, choose degree of regularity to the little omega, where omega is the linear algebra constant. So all we really need to do is compute this degree of regularity to characterize the number of field operations to compute the Grosvenor basis. And what is the degree of regularity? Well, when you're talking about an FP graded algebra, which is what is this FP x1 through xn thing, there's this thing called the Hilbert polynomial, which we don't worry about it too much. But basically, you just want to find the index of the first non-positive coefficient of this polynomial, and that's the degree of regularity. So you just need to estimate these coefficients and find the first one that goes non-positive. Great. And you might be asking, like, why are all these definitions with respect to homogeneous polynomials when we don't have homogeneous polynomials? And Albrecht says the following definition for inhomogeneous systems. He just considers the highest component that is homogeneous. So if f is 1 plus x1 plus x1 x2 plus x1 squared, then homogeneous fh is x1 x2 plus x1 squared. It's the highest degree component that's homogeneous. And we just say a sequence f1 through fm is semi-regular, meaning it has this characterization, this Hilbert polynomial characterization if this highest order part is semi-regular. Okay. Oh, thank you so much. So hopefully, sorry if I went through this really fast, but I think we only have like 30 seconds. So basically, what are we saying? As a recap, all the world-known definitions. We just need to compute the degree of regularity, which is to estimate the runtime. And how do we compute the degree of regularity? We need to compute this index of the first coefficient in this polynomial that becomes non-positive. So before we do that, let's make a quick simplification to remove this linear guy. So this linear guy just says, again, the number of error-ridden equations is t. So we just note that alpha 1 can be expressed in this format, just rearranging. And then we're just going to substitute for alpha 1 to eliminate one variable and one equation. And now all the equations are of degree 2. And after the simplification, the Hilbert series, so the ring we're working in is still over n plus m variables. So it's just this expression, just from the previous slides. And we need to compute the degree, the index of the first HD that is non-positive. That's our degree of regularity. And fortunately for us, Sun, Tabuchi, and Abe performed the same computation for a different polynomial system from binary LWE, and I believe that this saddle point approximation they used is also attributed, you can find in the work of Bardet et al. And it's basically some saddle point approximation, and it really boils down to this expression here in the analysis. So if we just plug in our E's and V's, we see that the degree of regularity in our setting for our system F comes out to order m. This term right here is n to the 1 plus alpha is order m, and which is bad. So it means our attack is exponential time under semi-regularity, assuming that our system F is semi-regular. Okay. And the other question we had was, can we directly increase the rank of the Macaulay matrix? So this is why we adopted the Macaulay matrix view. Oh, I'm so sorry. The observation is that the alpha I variables are indicators for sparse errors. So if I multiply enough of them, most of these are 0, they'll become 0. So we can actually add a bunch of high degree terms. You might be asking, like, why not add low degree terms? Adding low degree terms is the same as guessing where the error positions are in the first place. So we're saying we can add many high degree terms that hold with high probability. And how many of these can we add? We can add sub-exponentially many. So this is what this theorem is saying. And all of these will hold with pretty high probability. And we have no idea how these equations affect the rank of the Macaulay matrix, but this is kind of a direct way that we were hoping to increase the rank of the Macaulay matrix at lower degrees of expansion. So some discussion points. In general, like, estimating the rank of even a standard Macaulay matrix is pretty challenging. One, for example, even estimating the Grosvenor basis runtime is challenging in general. It's only because of the semi-regular assumption that we actually have a rough heuristic. And we really mean rough heuristic. And we have this hope that introducing high degree equations might boost the rank, but it's actually pretty hard to analyze how this changes the Macaulay matrix rank. We don't know how to lower bound it. We ran a few experiments. It's definitely rank deficient, but we can't run it for higher order terms because there's a sub-exponential or exponential blow up in the size of the Macaulay matrix. You have this like n plus d, like, you know, all the monomials of up to degree d, and this becomes horrible to run in practice. So it's hard to experimentally see. And yeah, just wanted to wrap up. I'm like 3 minutes and 30 seconds over. But we want to recap by saying, like, what do? We want to throw out there a quadratic system of equations for LPN over large fields. And if we falsely assume that it's full rank, we get an order root m, we show that order root m expansion is sufficient, which means we have this really nice sub-exponential attack. But if we assume semi-regularity, then we have only an order m expansion. We require order m expansion, we only get an exponential time attack. And some questions we have are, is there a clever way of increasing the rank of the Macaulay matrix, knowing your polynomial system? And there's another question, which is, this question is related to, in general, can you somehow lower bound the rank of a Macaulay matrix? In general, this seems like a really difficult question. And another question is, we proposed adding random high degree equations that hold with high probability, but we have no idea how to analyze the rank of this Macaulay matrix. And then finally, we have a question of, is there a better system of equations for LPN over FP? Yeah, I think that wraps up my, talk. So that's it. Thank you so much.
we have time for one question. If someone has a question.
Yeah.
Can you go to the mic? Sorry, for the people virtually can hear you. Thank you.
Hi, thank you for the
Yes.
talk. Thank you very much. What kind of experiments have you performed? Is it like magma computation? Is it like...
Yeah, great. So we didn't have access to magma. We did
Okay.
most things in Sage.
Okay,
So Sage, I believe the backend is either Singular or Macaulay 2.
and so you compute the Gromner basis, or you construct the Macaulay matrix by hand and you...
Yeah, so
compute the rank?
we did both. Compute the Grosvenor base is like super simple. It's like one line of code because it's like built in. And also setting up the Macaulay matrix is also pretty simple too. So we did both. Both scale pretty poorly. You can also compute, it estimates for you the degree of semi-regularity, but we really want to, for these experiments, we didn't want to just estimate degree of regularity. We wanted to see if there was an actual way of computing the rank of this matrix we're looking at. And I believe there's like maybe one paper I saw online about like computing the dimension of the left and right null space of Macaulay matrices, but it was not at all clear that it's hard to extract the relevant bits of information from that paper. Any other, oh wait, we don't have more time.
Well, no, if there are any other questions. All right, let's thank our speaker again.